I want to try and figure out some more Laplace transforms without actually doing the integrals, or at least with doing as few of the integrals as I can get away with. So let's consider a derivative. A derivative of the function after the transform. Well, that would be the derivative with respect to s. Because after we do the transform, s is the only variable. Wait a minute. This is what I get by doing the integral. Let me just write this down for a minute. My big problem with this is figuring out how the hell to do this derivative of an integral. But I get to cheat. If the function has a Laplace transform, in other words, if this f of t is of exponential order, then I can switch the integral and the derivative. My buddy Gottfried Leibniz came up with that. And this regular derivative, because now I'm going into this integral, and this integral integrand has two variables, becomes a partial derivative. It's still an s, though. Now, I don't actually want to do this integral, but I would like to do the derivative. What happens when I do that partial derivative? It's easier than you think. The only piece that has an s in it is the exponential, right? Everything else is t's, which means they're like constants. I can leave them alone. So I just need to take the derivative of e to the thing t, or in this case, e to the thing s, because s is my variable. What's the derivative of e to the stuff s? One over comes from the logarithm. This is the exponential. T. Because it's chain rule, e to the stuff and then the derivative of the stuff, but I'm only doing the derivative in s, so the minus t is a constant. Okay. I'm going to rearrange this ever so slightly. Let's put that t next to the f and put the minus sign outside. Hang on a second. The definition of the Laplace transform is you take the integral from 0 to infinity of e to the st, e to the minus st times stuff. Isn't that integral a Laplace transform? As a matter of fact, this integral is the Laplace transform of that. Holy crap, wait a second. The left-hand side of this equation was f prime of s. That means that I can actually write this underlined expression, the Laplace transform of t times f of t is minus the derivative of the Laplace transform of f of t. Every time I get an extra t on the function inside, that's like taking a derivative. By the way, if I had a t squared in there, I'd write it as t times tf of t. And that extra t would tell me to do the Laplace transform again, derivative. So I can generalize this. The Laplace transform of t to the n times f of t. Oh, if I do this derivative again, I'm going to get another minus sign, aren't I? It's got two minus signs, going to make it plus. If I do it a third time, I'll get a minus. I'm going to get a minus that flips back and forth like we do in power series. I'm going to get a minus 1 to the n. And then I'm going to take the nth derivative with respect to s of f of s. Minus 1 to the nth derivative of the Laplace transform of just ordinary f of t. All of the t to the n part goes away. Okay. $64,000 question. Why do I give a flying? So what? Well, the so what is based on the fact that we saw places where we had t times some function, or t squared times some function, or t cubed times some function in our differential equations in our non-homogeneous term. I kept doing undetermined coefficients and variation of parameters and all those integrals, and now I have a way around it. If I have the function t cosine 2t, and I want the Laplace transform of that, that extra t in there tells me to use this rule. So I say to myself, the correct answer for this Laplace transform is minus 1 to the first times the first derivative of the Laplace transform of cosine of 2t. But cosine of 2t is on my formula sheet. What is the Laplace transform? Cosine of 2t. Inside the back cover of the textbook, on our Canvas page, take the formula sheet. You should have the formula sheet because that's the one you get on the exam. You should be used to looking things up on that. Aha. Which means I need to do a derivative. Ladies and gentlemen, I give you Calc 1. No crazy ass integral, no partial fractions, none of that. Just take a derivative. 3 cheers for the quotient rule, people. You know how to do this derivative. Given the fact that things like products of e's and sines are on my formula sheet, products of e's and cosines are on my formula sheet, I could actually do that and add extra t's into them. T squared or t cubed or whatever it is without having to do the variation of parameters idea or the undetermined coefficients, where I had to do all those crazy Ronskins and integrals. This is a lot easier. No simultaneous equations yet. It's pretty good. This one's disgusting. Except it really isn't. The extra t tells me I'm going to do a derivative. It's t to the first, so I'm going to do a first derivative. That's minus the derivative in S of the Laplace transform of e to the 2t sine 6t. And that's on my formula sheet. It's 10, 11, somewhere in that range. E to the AT sine BT. Well, A is 2, B is 6. Off I go. A over S minus A squared plus B squared. Oh, A is 2. I just write the number in. The other way I could remember that is I could remember, hey, sine is A over S squared plus A squared. And the e to the 2t means I shift it by S minus 2. That's what we were talking about last week. Wait a minute. This is just a quotient rule. I know how to do this. Top's a number, so it'll probably be easier for me to do this derivative with the chain rule. S minus 2 quantity squared plus 36 to the minus 1. Hey, I'm going to get a negative, and a negative, that's going to be positive. 6 times ugly junk to the minus 2 times the derivative of the inside. The derivative of 36 is 0. The derivative of S minus 2 squared is 2. S minus 2 to the first. Again, times the derivative of the inside. The derivative of the inside is 1. All of this stuff is to the negative 2 power. It goes on the bottom. S minus 2 quantity squared plus 36, all squared. The top is 12S minus 24. Example 1 in the text actually does one in variables. Page number for operational 2. Page 315 leaves it as sine of kt. And it does not just t, but t squared and t cubed. So there's an idea here of trying to generate a pattern so that I can try and be able to work backwards, because it's the inverse transform. It's usually a little more difficult. Again, my goal is to solve differential equations. So let's put this sucker to work. Y double prime plus 9y equals cosine 3t. Y of 0 is 2. Y prime of 0 is 5. Now, here's the fun part. This is a second order differential equation. I could solve this using nothing but the undetermined coefficients method that we did last exam. I don't need Laplace transforms to do this. But if I do it that way, I need reduction of order or undetermined coefficients or variation of parameter. I need the extra step. But it's easier if I do the Laplace transform. What happens to my second derivative here when I take the Laplace transform? To the formula sheet. Laplace transform of a derivative. And then I get 9 Laplace transform of y. And on the right, I get Laplace transform of cosine of 3t. What's the Laplace transform of cosine of 3t? Now, y of 0 is 2. So this becomes 2s. Y prime of 0 is 5. I have Laplace transform of y times s squared plus 9. And over here, I have s over s squared plus 9. Move these pieces over, then divide. I'm going to do them as 3 fractions. So I get the Laplace transform of y is 2s over s squared plus 9 minus 5 over s squared plus 9 plus s over s squared plus 9 quantity squared. And this part right here, this part makes me go, wait a second. Just a second here, boys. This kind of looks like it should be the derivative of something that looks like this. Power rule, right? Stuff to the minus 1 should be stuff to the minus 2 when I take the derivative. So I claim this is somehow the derivative of something that looks like those pieces. What is s over s squared plus 9 quantity squared the derivative of? Wait a second. That just means you have to integrate it. I can integrate. Not only can I integrate, this is a Calc 1 integral. It's a U sub. How do I do this integral? which means du is, I don't have a 2, so I need a 1/2. So then I get the integral of u to the -2, which is negative u to the -1, right? So that's negative 1/2 s squared plus 9 to the -1, or negative 1/2. 1 over s squared plus 9, that looks exactly like that, doesn't it? The 1 over s squared plus 9. This is 5 over s squared plus 9. That's still the same idea, right? Okay. The Laplace transform of y can now be thought of taking the inverse transform of all three of these. Hang on a second. What's the inverse transform of s over s squared plus 9? What's the inverse transform of 1 over s squared plus 9? And then I got to figure out how to deal with this. But these two I know, I think. Where do you see s over s squared plus 9 on the formula sheet? I won't see it as over s squared plus 9. I'll see s squared plus a squared. Cosine. So this is 2 cosine of 3t minus. What about number over s squared plus a squared? Except that the number on top isn't a 1, right? The number on top is an a. Means I need a 3 on top. If I have a 3 on top, I'm going to get a 1/3 on the bottom. So I get 5/3 sine 3t. Now, I know that this thing is 1/2 the derivative of this. That looks like this. The fact that it's a derivative means when I do the inverse transform, I get an extra what? Say it again. A t. But I needed a 3 on top here, right? 3 over, so I got that 1/3, right? So now I'm going to get 1/6 because I need the 3, and I'm going to get t sine 3t. If we were doing this back in the last chapter, let me go back and think about the way I would have done this without Laplace transforms. Ready? I'm going to go back up to the top. I would have started by solving the corresponding homogeneous equation, right? What's the corresponding homogeneous equation? Which gives me r equals plus or minus 3i, which gives me cosine of 3t and sine of 3t. And then I say, oh, I need to do the other side. The other side already has a cosine of 3t. What do I need to do? I need to multiply by an extra t. But that means I'm going to get t cosine 3t and t sine 3t. And then I need to plug those back in and solve for the particular solution, right? And that's where I get this part. The coefficient of the cosine of 3t is 0. The coefficient of the sine 3t, t sine 3t part is negative 1/6. But I didn't have to do all the extra derivatives this time. In spite of the fact that I had to do this extra piece to look at one derivative, I didn't have to do the first derivative and the second derivative with the product rule 4 times. It's easier. Well, it's algebraically simpler. It's just not trivial. Examples 2 and 3, page 316, 317. There are 2 more versions of this in the text. This was problem 11. Questions? Yes, sir.
I don't know.
74. $74. This way? Well, I think this is probably better as a step function than it is trying to identify it as the derivative of something, right? So I think this wouldn't have worked for that part. It's not a bad idea, but I'm looking at that f of t and I'm going, I'm not sure what I'm going to get in the Laplace transform. And I have a step right in the middle of that problem. I think I should do the step function version. We keep doing integration by parts on a bunch of these things. Integration by parts is a pain in the ass. But integration by parts is done because we're multiplying inside my integral. So one of the things that came up in looking at integration products, something you either will see next semester in probability and stats, or you've already seen because you've already taken it, is the idea of the convolution of two functions. This is where we kind of mix the two functions together, multiplying in different directions. I'm going to define f star g of t. And this star operation is not multiplication, but it's a kind of way to generalize ideas. And we're going to integrate from 0 to little t of f of, I need a dummy variable. The textbook, in an effort to piss me off, uses the Greek letter t, tau, which means I have t's and taus in the same problem, and I always pick them up. So I'm going to change the letter. This is what I mean by multiplying in different directions. This part, z, goes from 0 to t, right? Z is going this way from 0 to t. What's this doing? Well, when z is 0, this starts at t and goes the other way. We're really trying to multiply these functions together like they are passing each other. Now, before you freak out on me and go, why the hell would you want to do that? Laplace is working on differential equations because he's studying vibrations in physics. Who's taken physics of waves? It's in physics 2. You saw the waves. Did you do the experiment where you take the string and you flick it from one end and then you flick it from the other end and the waves pass each other? Interference of waves. That's what convolution is doing. It's measuring the way the functions as waves interact with each other. I am the first person to tell you that this is a weird as hell idea. So I went and got an expert. On our Canvas page, I have a link to a video by Grant Sanderson, 3 blue, 1 brown, on convolutions. He's doing it from a physics perspective and a probability expectation. He's talking about expected values. And there's this lovely discussion in Prob and Stats about the expected values of 2 random variables as opposed to 1. For most of you, this is in Prob and Stats 2, which means it's not next semester, it's next fall. So you've already taken it, one of the 2. The actual discussion of convolutions is right about here, about the 10-minute mark, and he walks through why this works for any 2 functions. I heartily recommend this video. It's not terribly long, and I think it's a very good visual interpretation of what convolutions do. But the reason I want to do convolutions is because it turns out that when I convolve functions, it's easier to work with their Laplace transforms. I should do one of these just to show you the way the integral works. So I'm going to do a simple one, quote unquote. We're going to let f of t be 4t and g of t be 3t squared. And I'm going to do this integral. F convolved with g is the integral from 0 to t of 4z times 3t minus z squared dz. You are welcome to use tau if you really like. Me, I don't care. I got a 4 and a 3. I'm going to pull out a factor of 12. Integral from 0 to t, z, t minus z squared dz. Let's multiply it out. I get zt squared two times t times z times another z. And then I get z squared and another z, so I get a z cubed dz. This is a power rule integral. I'm integrating z. That means t is a number. And so this becomes right here. Aha. Z squared over 2t squared. Here. Oh, don't forget the t. Right. And then here, I get z to the fourth over 4. There's no t on that part. But all of this is evaluated. Z equals 0 to t. So I'm going to put in, for every z, I'm going to put in a t. Here, I get t to the fourth over 2. Here, I get t cubed times t, I get 2 t to the fourth over 3. And here I get t to the fourth over 4. Then I put in 0 for all of those z's, and I get 0 everywhere. I am going to go ahead and multiply through by the 12 because I think that'll make my life easier. This is 6t to the fourth minus 8t to the fourth plus 3t to the fourth, which is just t to the fourth. Now, sneaky. What is the Laplace transform of t to the fourth? There are two different ways to do this. I have t to the n, right? But the other way I can do this is I can say, hey, what's the Laplace transform of 1? I would need to take the fourth derivative of that. But every time I take a derivative, I get to multiply by the power, right? T to the s to the negative 1. So I get negative s to the negative 2. And then I get 2s to the negative 3. And then I get 6s to the negative 4. And then I get 24s to the negative 5, which is the same as 4 factorial over s to the 4 plus 1, isn't it? Which is exactly the formula in our textbook. Whew. Put a little star next to that for the moment. There are two important results that get used with convolution, but the first most important thing I need to re-emphasize is that convolution is not multiplication. Because if I think of f star 1, that would be the integral from 0 to t f of z times 1 dz. That's not f, that's the integral of f. And there are very few functions that are equal to their own integral. So convolution is not really multiplication. It's a generalized multiplication. And it happens to have some really nice properties. And those properties look like multiplication. F star G is equal to G star F. It's commutative, just like multiplication. It's associative. F star G all star H is the same as F star the quantity G star H. It distributes like multiplication does. F star G plus H is F star G plus F star H. And if I have a constant, I can put the constant wherever I want. C times the convolution F star G is the same as CF star G is the same as F star CG. I put the constant wherever I want. However, big however, my absolute favorite thing about the convolution is the Laplace transform. Go back to our example from a moment ago, where I asked you to look at the Laplace transform of t to the fourth, right? We started that problem with f of t was 4t and g of t was 3t squared. What is the Laplace transform of 4t? What is the Laplace transform of 3t squared? Well, that's 3 Laplace transform of t squared. So that's 3 times what? or 6 over s cubed, right? I asked you to put a star next to a line at the end of our giant convolution calculation. Cody, what are you shaking your head at? 4 times 6 is 24. S squared times s cubed is s to the 5th. Son of a bitch. The Laplace transform of f star g is the Laplace transform of f times the Laplace transform of g. Convolution becomes multiplying in the Laplace transform. If I can look at a function and say, hey, wait a minute, this function is something that should be a convolution, then I can take that even if I don't have the function written out explicitly, even if the function is written as an integral. This problem is taken directly from the text. Find the Laplace transform of the integral from 0 to t, tau, e to the t minus tau, d tau. See why I hate having taus and t's in the same damn problem? Twitch, twitch, twitch. But I look at this and I say, wait a minute. F of t, f of z, e to the t minus z, this is the convolution. This thing is the convolution of f of t equals t and g of t equals e to the t. I don't have to do the convolution integral. I can say, oh, this is really the Laplace transform of t star e to the t, which means it's the Laplace transform of t times the Laplace transform of e to the t. And we know those. Laplace transform of t is 1 over s squared. The Laplace transform of e to the t is 1 over s minus 1. But my real powerful part of this is the inverse transform. It's not going this way, it's going backwards. If I see something that is the product of two Laplace transforms, and I do the inverse to it, I get f of t convolved with g of t. Which means if I say to myself, hey, I'm taking the inverse Laplace transform of 1 over s cubed s minus 1. Now, my first reaction might be, this is going to be a really shitty piece of partial fractions, isn't it? That's going to absolutely suck to do partial fractions. It's not hard, but it's a lot of ugly algebra. You all have been bitching at me about how ugly the algebra is. I understand that. But I can say to myself, wait a minute. This is 1 over s cubed times 1 over s minus 1. What's the inverse transform of 1 over s minus 1? And what about as cubed? 1 over s cubed here. Oh, wait a minute. If it's s cubed, it should be a 2 on top, right? So that's 1/2 t squared. L inverse 1 over s cubed is 1/2 t squared. L inverse of 1 over s minus 1 is e to the t. I'm done. I don't have to do partial fractions at all. I know the correct answer for this inverse transform is 1/2 t squared star e to the t. The problem is, what I really have to do is to do that integral. If I want to know what the answer is, I need to do the integral from 0 to t, 1/2 z squared e to the, I got to go back and look, make sure I wrote it down correctly, t minus z dz, which unfortunately is integration by parts twice. So here's a trade-off. Would you rather do the partial fractions, or would you rather do integration by parts twice? Either way, it works. On our Canvas formula sheet, there's our convolution setup. There's our derivative setup. These are the two we did so far today. I'm going to do this one, but it's going to be rushed because I'm about to run up against the clock wall. So this should be something you read carefully on page 321. When I have a function that's periodic, when we do a Laplace transform, we're integrating from 0 to infinity, right? But if I have a periodic function, I really only need to know what it's doing on one period. And then I can just average that out over the whole thing. This 1 over 1 minus e to the negative st. That capital T is my period. This is where the period comes back in and bites me. When I'm doing trig functions, that would be a 2 pi. But I can do any sort of repeating function, like a sawtooth function, or a 0-1 on-off step function, a pulsing function. Things like wrong page. Things like this, a square wave. It's a signal that goes on, off, on, off, on, off. Gee, I don't know anything that does that. You listen to damn fire alarms. I want to be able to do this sort of transformation. But again, I can go through an example. There's a lot of algebra that goes into this because this stuff rarely looks pretty. When I do the antiderivative, I get some examples that are just disgusting. The example on page 323, when I did it, I set it up ever so slightly differently algebraically, had a very different looking answer. Took me about another 4 lines to show that my answer was the same as the answer in the back of the book. Page 329, example 9, example 10 also does this. Please read them carefully. There are literally 2 more functions here, 20 and 21. That's Monday. Then we're actually done with this chapter. Or at least with what I'm going to do. But that delta function, that's an interesting one. We'll talk about it on Monday. Happy Halloween. Enjoy your weekend.